nanohub.org.
Okay, so now we're going to talk today about three important calibrations that most of you need to know while making any AFM measurement. And the three calibrations are the following. The first is what's called the Z-piezo calibration. The second is the cantilever deflection calibration. And the third is the cantilever stiffness calibration. Now, you have to keep in mind that in an AFM, when you move the cantilever close to the sample, you're applying a voltage to a piezo actuator, right? But how do you know how much the piezo actuator moved? So, in the previous examples in the last class, we talked about F versus Z. Z was somehow magically always in nanometers. Well, how do you know that? How do you know how many nanometer did it actually move forward by? This is an important question. I mean, because in reality, what the AFM controller knows is that it applied 1 volt to the piezo. Now, how did that 1 volt convert to a 10 nanometer Z displacement is not very clear. How do you know it for sure? Now, it turns out most AFM systems have a conversion number inside them that convert the voltage they apply to the Z piezo into nanometers of piezo displacement. However, those numbers are not necessarily correct. So every time you do an experiment, preferably every month, you need to calibrate your Z piezo. Same thing with your XY piezos. When you scan, you're moving X and Y direction of the piezo. And, those images come in nanometers. Well, how do you know that truly is the right nanometer? Because really what the system does is applying a 10 volt sawtooth wave to just scan the sample back and forth. But how do you know that it is moving as much as advertised, right? Or as it appears in the images. So that's what the Z-piezo calibration is really about. The second calibration is cantilever deflection calibration, because remember, the whole premise of measuring interaction forces is as follows. When we have a photodiode, what you measure is the bending angle of the cantilever. So this is a very important point, because if you look at the trigonometry of the process, if this is a cantilever, if it just moves up and down rigidly without bending, if you look at the trigonometry, the laser spot position on the photodiode barely moves, hardly moves very, very little as you move this up and down. On the other hand, as this bends, right, if you look at the trigonometry, there's a big amplification of this rotational bending signal. So the laser spot comes here, if it bends, it moves and displaces by a large amount in the photodiode, which is why what a photodiode measures is not absolute up and down position, but rather rotation angle or bending of the cantilever. So the logic, though, is the following. I showed you when you apply a point force, there is a linear relationship between the bending angle and the deflection. So it's okay as long as you measure the deflection, because deflection is linearly proportional to the transverse deflection also. So while we measure this, in principle, it is linearly proportional to the amount the tip has bent up by, right? But what comes out of the photodiode is a voltage, right? So how do you convert that voltage into what you want to measure, which is tip deflection? How do you do that? That's the main question. And that's where we do cantilever deflection calibration. And lastly, the cantilever stiffness calibration, we'll talk about that in some more detail now. So we'll go through these three calibrations one by one. The Z-piezo calibration, what you need to do here is, what you need to do is to buy what are called calibration gratings. And there are many suppliers of AFM calibration gratings. There are many kinds of calibration gratings. There are some that are designed mostly for calibrating the Z-piezo, like the one on the left. There are some, like in the middle, designed for calibrating X, Y, and Z, all three piezos, for example. And then there are some, like on the right, that are designed for calibrating things like related to friction force microscopy, like if you want to know what angle you're twisting by and so on, right? Right, so you can buy these, and all of you should have them if you do atomic force microscopy. So the idea of these gratings is the following. They have known dimensions, right? So when you buy the grating, they're going to tell you the grating has a certain height of, let's say, 10 nanometers, plus, minus, and they give you an uncertainty with it. And I highly encourage you, if you buy it from a manufacturer, if you pay a little extra, you actually get a certificate of which quantifies the uncertainty associated with it. Because people can quantify the uncertainty, to within the wavelength of light. So it's a traceable standard. It's very important because, they might say this calibration standard is 10 nanometers high, but in reality, it's not 10 nanometers high. It's going to be 10 plus minus 1 with a probability of 90%, right? So the idea then is going to be that you take this known dimension and scan in contact mode, right? Now remember, when you first scan this image in contact mode, your height is going to be in volts. It's the volts applied to the base of the piezo to keep the deflection constant. So you're going to get volts versus volts applied to the X piezo, volts applied to the Y piezo, right? That's the basic image. Somehow the AFM system is converting volts, X, Y, Z into nanometers, nanometers, nanometers. How is it doing it? Or how do you make sure the conversion is correct? Well, you got the image in volts versus volts versus volts, and you know the dimensions of this grating in the XY direction and in the height direction, right? So you say, okay, in my image, I'm measuring the width of this particular object as 10 millivolts, and it's supposed to be 100 nanometers. Therefore, along the X direction, 10 millivolts equals 10 nanometers, right? You do the same along the Y direction. You do the same for the height, okay? So this is how you convert it, and this number is usually buried somewhere inside the AFM software, this conversion. Because if you don't periodically do this, you're using a conversion constant that was used a long time ago by somebody else. And with time, these piezos change and, things happen. And so I would encourage once a month you do this calibration grating on your AFMs, just to be sure. Now, having said that, there are some new technological developments in AFM. One is the use of closed-loop piezo stages. If you buy new AFMs, you're always going to get closed-loop piezo stages. What closed-loop piezo stages do is they have built inside them a sensor that detects how much the piezo is actually moving, right? So you apply a voltage, but it actually detects in nanometers how much is actually moving. So it's a closed-loop system. So you don't have to apply a voltage and try to figure out how much it moved. Rather, the system feedback loop is doing it for you. Of course, this makes life easy. At the same time, you know what problem happens if you trust too much in technology. If you trust too much in technology, the problem is when it fails you, you don't know it, right? And you keep going. So even though you use closed loop, the idea is every 6 months, my suggestion would be to calibrate these things. Because what if the sensors that are embedded inside these feedback loops, what if they stop working? How do you know? You never know. So you just have to, I think, still every 6 months or at least a year, do this kind of calibration, even if you have closed loop systems, okay? So everyone clear about Z piezo calibration and XY piezo calibration using calibration gratings, yeah? Okay. The second is the cantilever deflection calibration. So as shown in this figure, what is happening is when you sort of press on a sample, the cantilever bends, and the bending angle is measured as a voltage output from the photodiode. What we need to do is to convert the voltage output to the up and down motion of the tip, deflection of the tip in nanometers. Okay, that's what we have to do. How do we do this? The standard way of doing this is to do what's called a FZ curve on a hard sample. By the way, this conversion has to be done even if you have a closed-loop piezo. This has nothing to do with closed-loop piezos, okay? This is something else. So what you would do is you would move either, if you have a sample scanning system, your sample moves up. If you have a tip scanning, your cantilever base moves down. You move the Z on a hard, and then approach the cantilever on a hard surface. And you touch the hard surface. Now, we discussed this in the last class, but if you're on an infinitely hard surface, once you're in contact, when you move down by a certain Z distance, that's the amount the cantilever deflects up relative to the base, right? You go down here, if I move this down by 10 nanometers, well, this tip is 10 nanometers above the base, right? If this surface is infinitely stiff. In other words, if you're on an infinitely stiff surface, any Z motion goes into cantilever deflection only. There's no sample deformation. So in other words, if you do an FZ curve on an infinitely hard sample, along the y-axis you're measuring volts, along the x-axis you got piezo displacement in nanometers. The key thing is on an infinitely hard substrate, the straight line needs to be 45 degrees. it has to have a 1-to-1 slope. Remember, because whatever you move in z must be whatever it deflects up by, right? The tip. And so that's what you use. So what you would simply use is look at the slope here. This slope is going to be in millivolts per nanometers, and this slope allows you to convert any millivolts of photodiode output to nanometers of tip deflection. So you use this idea that on an infinitely hard substrate, this angle should be 45 degrees. When plotted nanometers to nanometers, it should be 45 degrees, okay? So what is an infinitely hard sample? This depends, you know. If you're trying to measure the stiffness of a very stiff object, then this calibration needs to be done on an even stiffer object, right? So let's say your job is to figure out the stiffness of mica using AFM, elastic modulus of mica using AFM. That's difficult because to do the stiffness, you have to do this calibration on something else. This calibration assumes that the sample is rigid, infinitely rigid, right? So if you do this calibration on mica and then try to do stiffness on mica, what elastic modulus are you going to get on mica? You're going to get infinity because you've done the calibration assuming mica is infinitely stiff. So whatever object whose stiffness you're measuring, your cantilever deflection calibration has to be done on a sample that's much, much stiffer than that. And if God forbid, if you're asked to do elastic modulus of mica, which I hope none of you is asked to do, which is terrible, very difficult to do. It's very stiff. You would have to use something like, I don't know, osmidium or sapphire or something like that, which are at least Young's modulus that's 4 times greater than that of what you're trying to study, okay? So keep that in mind. Of course, if you're doing soft samples, mica, silicon is typically okay. All right, the last calibration of interest is K, which is the cantilever stiffness calibration. In principle, if we go to simple beam theory like we discussed a couple of classes ago, there is actually an expression for the cantilever stiffness K sub C, which is 3EI over L cubed, where E is the Young's modulus of the material. In most cases, we're using silicon, and silicon has a pretty well-defined, at least monocrystalline silicon has a well-defined, reasonably well-defined elastic modulus at room temperature. And I is this quantity BH cubed over 12, and L is the length. So you could use that, but the main problem is that when you buy these cantilevers, you don't really know H. You don't really know the thickness of the cantilever, because if you look at the underlying technology used for producing cantilevers, there's an etching process. You have to etch away underneath the cantilever to release the cantilever. Etching processes are notoriously difficult for controlling the thickness of what you're trying to etch away, because it's a chemical reaction. How to control it in a manner so that, how do you ensure that exactly after 5 minutes of etching, you removed exactly that much material, so you're left with a certain thickness? This is very hard to do precisely. And as a result, the biggest variability that happens when you go from cantilever to cantilever is variability in thickness, and from wafer to wafer, in fact. So even though a manufacturer tells you their cantilever is 1 Newton per meter, it'll never be 1 Newton per meter. It can be anywhere between 0.25 and 5 Newton per meter. Huge variability. You can get hundreds of % variability in cantilever stiffness from what a manufacturer reports. This is the problem, okay? So very early on, people realized that you need to figure out how to measure K for every cantilever. And just because you measured stiffness for one cantilever doesn't mean that all the cantilevers in the batch you purchase are going to be the same. Within the same batch, you start getting variations. In fact, within the same wafer, as you go look at stiffnesses in the center of the wafer to the edge of the wafer, you'll start getting variations in that. So you have to, for every cantilever, measure the stiffness. But if you think about it, measuring stiffness of an object, spring constant of an object, is something I suppose we've been doing since high school, right? I mean, if I give you a spring and I ask you, tell me what the spring constant is, you will say, oh, it's very easy. I just need to apply a known mass or a known force. And how do you do known force? Well, you can get masses that are pretty well known, and got a gravitational constant. You just add it, you measure how much it extends by, and you're done, right? You've got the spring constant of the spring. Now, let's take this concept to the nanoscale. Can we hang a mass at the end, known mass? Well, think about it. Gravitational forces scale with volume, right? When you choose a very small thing, the force that the gravitational force due to a small sphere on a cantilever basically is non-existent. It's extremely small, okay? So trying to use gravity and hanging a mass, that concept doesn't work because at nanoscale, gravity doesn't really play much of a role, right? It's all surface force dominated everything. So then what do you do? So the question is, how do you apply known force? What do you do? So the objective should be to apply, let's say, 10 nanonewtons of force and measure the deflection. So you're stuck because we don't really have standards. There is, in fact, no method to generate a standard force of 10 nanonewtons. It doesn't exist. And this is the problem. So many indirect methods have been developed to calibrate cantilever stiffness. The other thing to keep in mind is that there is a difference between measuring the stiffness, when you apply a point force and this just gently bends up, to when you're talking of stiffness of an eigenmode of a cantilever. Because when you're doing dynamic AFM, remember, the shape in which it oscillates is a little different. It's not this nice cubic curve you get. And so the bending and the strain energy associated with a cantilever oscillating in an eigenmode is different from that you would get when you have a point force. And so the stiffness, i.e. the spring constant, clearly depends on the shape in which it bends, and the shape in which it bends depends on the eigenmode. So if you do static, you'll get a different value. If you do dynamic in the first mode, you'll get a different value of spring constant. Second mode will be a different value. So really, there are many different spring constants associated with the cantilever. We refer to K sub C as the spring constant when you apply a simple point force and it statically bends. We call it the static spring constant of the cantilever. Then we have Ki, K1, K2, K3, representing the spring constants of the first eigenmode, the second eigenmode, third eigenmode, and so on. Okay? The question is, how do we figure all this out? And, well, even before we do that, many people will say, why do we need it? Because you actually don't need to know the spring constant to take an image. You can always take an image, right? You don't need to know spring constant to take an image. But any time you do anything quantitative and you need to know what force you're applying, you need to know what K is. Kc is. So when you do, this is one of the things you often see, when people take a contact mode image, I ask them, well, what force did you apply when you took that image? Most people will say, I applied 1 volt of force. Is 1 volt a force, a unit of force? It doesn't make sense because on the other hand, if you go through the calibration process, convert volts to nanometers of cantilever deflection, multiply cantilever deflection by the calibrated stiffness, then you know force in nanonewtons. Again, I emphasize it's essential to know the force in nanonewtons, not in volts, because nanonewtons gives you a feel of what regime of physics you're looking at. Volts do not give you any physical intuition about what forces you're applying. Remember, I told you things like, in AFM, you should never be applying more than 100 nanonewtons. 100 nanonewtons, you're basically bashing the sample completely. In fact, if you think about it, 100 nanonewtons of force, the tip radius is typically 10 nanometers. You apply 100 nanometers over an area of 10 nanometers in circle, you calculate the stress you're creating. It is more than the yield stress of most materials. You're applying a small force, but on an even smaller area. So the stresses are huge. Normal stresses are huge. Right? You easily reach a gigapascal with 100 nanonewtons of force underneath. So this is a problem. So you have to do forces in nanonewtons to know what regime of physics you're looking at, whether you have plastic deformations, you're elastic, or are you imaging the liquid surface as opposed to imaging the real structure, and so on. The other thing is, whenever you try to measure local elasticity or adhesion, well, if you don't know the spring constant, you're not going to get a good number. You don't know what number you're getting, right? When we start talking more about dynamic mode, you need to know as you're tapping on a sample what forces you're applying. All these things require you to know what the spring constant K is, okay? So you cannot really do anything quantitative in AFM if you just report the force in terms of volts. You can't do anything quantitative with that, okay? Because the same cantilever, you do a contact mode scan in 1 volt, someone else does it, they focus the laser somewhere else on the cantilever. 1 volt is not a constant that you can compare different AFM systems with because the conversions are different, their amplifications are different and so on. So Nanonewtons, nanometers are fundamental units with which you can compare measurement made in different AFM systems, for example, okay? Okay, so what are the different methods available for calculating stiffness? Many, many methods are there. Many, many methods. NIST, the National Institute of Standards and Technology, has finally come up with a stiffness calibrating device, which is traceable to, in NIST, they're very worried about every measurement being traceable to some fundamental unit like wavelength of light or forces, to some fundamental units, traceable standards. But this is not widely available. It's a MEMS device. Basically, you press on it, and it's a very well-calibrated MEMS device, and it just spits out the number of spring constant of your cantilever. But it's very expensive. It has to be used very carefully, and it's not available commercially. So over the years, people have broadly come up with what are called geometric methods. There are many different methods, but the Cleveland method and the Sater methods are the main geometric methods. And the thermal methods are Hutter and Beckhofer and Butt and Jaski's work, okay? We'll discuss those because those are the main ways of calibrating cantilever stiffnesses today. The Cleveland method is the following. The Cleveland method says that, okay, we don't know the stiffness of the cantilever, but if I add a known mass at the end of the cantilever, and if I look at the resonance frequency shift due to the known mass, remember resonance frequency is square root k over m for an oscillator. We don't know what k is, we don't know what m is, but if I measure square root k over m and then add a known mass, square root k over m plus delta m, where delta m is known, you can actually use that to eliminate m and get k out of it. And that's what they've done here. So what they end up doing is, if the added mass is uppercase m, you can calculate the spring constant K1. Again, this is the spring constant of the first mode because you're looking at resonance frequency. And, when you talk of resonance frequencies, you're talking of stiffnesses of that particular mode. It's going to be m divided by omega 1 prime is the frequency before you add the mass. No, how does it go? Sorry. Omega 1 prime is after you add the mass. Omega 1 is before you add the mass. Right? So it's a very simple idea. You've got an oscillator whose spring constant you don't know, whose mass you don't know. But if you just add a known mass on top of it and measure the shift in frequency, you can figure out what is the spring constant. It's a very nice method. It's simple. It's just using square root k over m. So the original frequency omega 1 is square root k over m of the cantilever. After you add it square root k over m plus this uppercase m, which is the added mass, and just using those two equations, you can back out what is the k of the cantilever. Okay? And so typically what is done, how do you know what mass you're adding? So what Cleveland came up with is you can buy these spheres, for example, that are metal spheres, or gold spheres, for example. You do electron microscopy, you figure out the radius, the density, bulk density of the material, so you can calculate the mass, right? But it's not convenient because you have to add a mass. How do you add a mass to the cantilever? You can't just throw it at it. So this has to be done either in an electron microscope or in a dark field microscope, and you have to sort of bring things together. Second question is, how are you going to stick the mass on? Cleveland said, you don't need to worry about that because surface forces will take care. It just sticks. Great, but you need to remove it afterwards, right? So all these things are there. It's not very convenient because it's invasive. You have to add something to it. The second geometric method is that of Sater. This, in my opinion, is one of the most elegant. I'm just amazed at how he was able to pull this off because, remember, we're talking of the most natural, intuitive way of measuring spring constant is you apply a force, measure a deflection. But the problem with the nanoscale is we don't have a source of a known force. There is no such thing that delivers 1 nanonewton of force constantly. This is a problem. This, on the other hand, is such an indirect method of doing it, and yet it works amazingly, absolutely phenomenal. And it's based on a completely different idea that John Sater, who's in Australia, came up with. And it's based on a very simple observation. And I mean, I can go into depth later, but the point is, you know what damping of a structure is, right? All of you know what damping. Damping literally means if I take a cantilever or a structure and I ping it, it's going to decay with a certain rate, right? That decay rate is connected to what's called the damping of that eigenmode. Now, for almost any structure, if you ask anybody who studies vibrations, right, they're going to say there is no way you can ever, from first principles, predict the damping of a structure. No, any person who does structural mechanics is going to say there's no way, because the amount of mechanisms involved that cause damping are just in a macro scale structure are tremendous. You know, you can have internal losses due to something vibrating. You may not have clamped it properly, so energy leaks out through here. There are many, many, many ways of energy loss that happens. You know, and by the time you put everything together, you might have a supercomputing working on all these loss mechanisms and might predict it okay for one particular case, but there are going to be no simple formulas for it. However, when you look at monolithic silicon structures such as AFM cantilevers, it turns out that the fundamental mechanism of damping is dissipation in the surrounding liquid. There's hardly any, I mean, in terms of comparison, as this oscillates in a surrounding viscous fluid, this contributes 99.99% of the entire dissipation. Internal dissipations due to defects are hardly there in comparison to this. Losses due to, you know, this vibrating energy going out into the chip itself, hardly. So 99.999 is basically due to viscous dissipation. So he pretty much came up with a theory that was able to predict what is the damping based on hydrodynamics, a fluid mechanics sort of study of this. And the numbers he came up with damping, or the Q factor of these cantilevers, was absolutely fantastic. It comes to within, I tell you, it comes to within 5% of what you might get from measuring things, for example. So using that idea, he noticed in a previous paper of his, so 1999 is this famous paper. It's been cited hundreds of times. Before that, in 1998, he had a paper on what is the frequency response of cantilevers when they're immersed in a liquid. And, you know, he came up with some interesting relationships. And then in the second paper, 1999, he realized that those relationships can be used to get to the spring constant of the cantilever without knowing what the thickness of the cantilever is. This is the key thing. The key thing is, as I said, the one thing we cannot trust from the manufacturer is the thickness, but we can trust the width and length data they provide, right? Because the length and width come from the mask that's used to prepare those cantilevers. The thickness is not decided by the mask dimensions. Thickness is decided by the etching process and the control of the etching process. So Seder's method utilizes basically information about just the length and the width which you can get from a scanning electron image, or you can take the manufacturer's number and it's within 5% correct. Okay? So let me step you through some of the essentials of this process. So the first thing Seder's method does is, if you know the frequency of a rectangular cantilever beam in vacuum, his theory is able to predict what will the frequency be in water or in any liquid. Okay? Now, I want to emphasize this with the help of an example. So the data on the top left is the resonance curve. This is the mechanical resonances of the cantilever. The curve in black is in air, and the same cantilever, when put in water, the blue is the curve in water. So what happens, obviously, is the resonance frequency shifts completely from when you're in air and go into water. And the same thing would happen, for example, when you go from vacuum to air. So as soon as you change the medium, it changes the natural frequency of a cantilever. And we'll discuss why. The other thing that changes from air to liquid is the fact that in air the curve is very sharp, but in liquid it becomes very broad. So what that implies, of course, is that the quality factor, or the quality factor, decreases in water compared to air, and in air the quality factor decreases compared to vacuum. Okay? So what Seder's theory did is he came up with two important formulas. One formula predicts what is called the added mass effect of the cantilever. The other formula predicts the damping on the cantilever due to the hydrodynamics, okay? So let's look at the first expression that is sort of important to understand. He came up with an expression when you have a cantilever with a rectangular cross-section, right? He came up with an expression for what is the hydrodynamic force per unit length of that cantilever, okay? So the cantilever is oscillating like this. What is the hydrodynamic force per unit length on the cantilever? And the formula is pi over 4 times the density of the fluid, rho f, times the frequency at which this is moving up and down. So the key observation is when you do fluid dynamics, what ends up happening is the added mass effect and the dissipation become frequency dependent. It depends on the resistance you get from the fluid, depends on how fast you're shaking it. And this is, again, you have to do fundamental fluid mechanics for this to figure this out, right? So the hydrodynamic force depends on the frequency that this object is moving up and down. Squared of that frequency times b squared. B is the width of the cantilever squared. Wx is the deflection at the location x of the cantilever, right? So the cantilever is vibrating like this. At some x locations, you're going to have small deflections. Near the end, you'll have large W. So W is basically the deflection curve of the cantilever in nanometers or whatever it is. So if you look at the units here, you find that gamma is this number called is a function called the hydrodynamic function. It's dimensionless, okay? So what he came up with was a very neat expression for the hydrodynamic function gamma for rectangular cross-section cantilevers. It's an analytical expression or a semi-analytical function which involves natural logs and stuff. But effectively, there's a closed form formula for that gamma that exists, okay? And it depends on the frequency omega. All right. Now, the key point is that as you move the cantilever up and down, the surrounding fluid applies force in two ways, right? One, it resists the motion. There's a viscous drag, right? So there is one component of force that the fluid applies in the cantilever that is in phase with the velocity. It's opposite to the velocity. It's resisting motion velocity, right? So it's a velocity-dependent drag force, if you will. There's a second component of force, which is called the added mass effect. What it means is, as you're trying to oscillate the cantilever, you're accelerating the surrounding fluid. There's a whole volume of fluid that you're carrying with you. So think of like a skin. It's not the cantilever's vibrating on its own. As the cantilever accelerates back and forth, you have to take into account the inertia of the surrounding fluid as well, which effectively adds mass, right? So the cantilever oscillating in water feels a lot more inertia than it does in air or it does in vacuum. So there are two components to this. And the way to think about this is, if the cantilever moves up and down as sine omega t, its velocity moves as cosine omega t, its acceleration moves as sine omega t again. So the force that the viscous fluid applies in the cantilever has a component that goes with sine omega t, which is the added mass component, or with the acceleration, and another component that goes with cosine omega t, which is the part proportional to the velocity. So, as most of you know, when you do trigonometry, you got sines and cosines. It's better to do e to the I omega t, right? I is the complex number. And if you do that, you find that you can write the hydrodynamic function gamma in terms of a real and imaginary part, okay? The most important thing is that the real part of the hydrodynamic function measures the added mass effect, which is, i.e., the force that is in phase with the acceleration, and the imaginary part measures the force proportional to the velocity of the cantilever, which is the imaginary part of the hydrodynamic function. So out here is this very general plot of this hydrodynamic function gamma, both the real and imaginary parts. The dotted part is the imaginary component, solid line is the real part, and he developed these exact semi-analytical expressions for these things, okay? Now, using these hydrodynamic functions, he was able to come up with, if you look at equation 2, he was able to come up with a relationship that connects the natural frequency of a cantilever in vacuum to what it would be when immersed in a fluid. So in vacuum, there's no added mass from the fluid, right? There's no fluid effect because it's in vacuum. And you can imagine that this process of trying to connect what the frequency would be in vacuum to what it is in a liquid requires you to use the hydrodynamic functions, right? So in vacuum, you have a certain frequency, but as soon as it's put in air or in any liquid, as it oscillates, now it has to push the surrounding air along with it, right? And so the frequency is going to change. And so this idea is embedded inside equation 2. So, I mean, we can look into Seder's paper for more details, but the idea is this, that if you tell me what is the frequency in vacuum, I can tell you I can predict what the frequency will be in any liquid using equation 2. How? I have to solve, if you give me omega vac, you give me density of fluid, density of cantilever, width of the cantilever, and thickness of the cantilever H, I can figure out what value of omega F satisfies equation 2. Now, this is not an easy calculation to do because the dependence on omega F is nonlinear. It's some function as you see out here, okay? So I would have to use MATLAB. You give me omega vac, I'd have to use MATLAB to figure out what value of omega F fits this. However, what Seder's thought was, well, that's a complicated thing to do. Because in reality, you don't measure the frequency in vacuum. In reality, when you do an experiment, you're measuring frequency in the medium. So that makes life simple. So in reality, when an experimentalist looks at this equation 2, they're going to say, gee, who cares about, this? Because I do measure the frequency in the fluid, as shown on these graphs on the left. So instead of trying to get omega F given omega vac, the more important question is, if you measure omega F, i.e. frequency in the fluid, what would the hypothetical frequency be in vacuum, omega vac? That's an easier relationship because these formulas are all known. So equation 2 tells you if you measure omega F, how do you get to omega vac? Okay? That's one step in this idea that he came up with. The second step in equation 3 is, again, when he did it, he was trying to predict what would the Q factor be of this cantilever when put in a liquid. And he came up with an expression in this previous paper in 1998 that connected the Q factor in fluid to the real and imaginary part of the hydrodynamic function, okay? However, in 1999, he realized you can invert that relationship. Why do you want to predict Q if you can measure it, right? It all started theoretically, let's say I know frequency in vacuum. Can I predict how it would behave in liquids? Which is great. But as an experimentalist, you're going to say, well, I can measure omega and Q in air. Why do I need to do this? So when you revert that relationship, equation 3 tells you how the quality factor that you measure in liquids, QF, along with your knowledge of this function, hydrodynamic function gamma R, how it can be used to get this quantity rho CH, okay, which is the areal mass of the cantilever. It's just a little mathematical manipulation, but it comes from, I just want you to understand, it comes from in his previous paper, he's trying to predict. Can I predict that you put a cantilever in a certain medium, what its Q factor is going to be? Then he realized that, well, you can always measure it. If you measure it, you can invert it to figure out what rho CH is, the areal mass of the cantilever. So, now let's see how we're going to get to K1, the cantilever spring constant, or of the first mode. If you look at equation 1, the equation on the left, I hope you all agree with me that if you knew the mass of the cantilever M1, and if you know the frequency in vacuum of the cantilever, then you do know K1. K1 is simply going to be m omega squared, yeah? Right? Because omega is square root K over m. Right. Well, he said that, well, if you think about it, and we have not shown this in detail, but the mass of the cantilever, it's not simply density times volume, because again, we're looking at mass while it's oscillating in this eigenmode, right? So there has to be a weighting factor. The whole thing is not moving up and down. The tip moves a lot more than the base. So when you take into account the shape in which it's oscillating, there's something called the suspended mass of the cantilever. It is 0.2427 times the overall mass of the cantilever. We'll do this in detail later, okay? Don't worry about it. We'll come to that formula. But the point is that M1 has in it this quantity rho CH, right? So his point was, look, from equation 2, I can plug in into equation 1 the expression for omega vac. From equation 3, I can plug in the expression for rho CH into the equation for M1. And you put it all together, and you have a very nice expression for K1. K1 is the spring constant of the first eigenmode of the cantilever. In terms of rho F, density of the fluid it's sitting in, the width of the cantilever, B, length of the cantilever, Q factor QF that you measure, times this hydrodynamic function, which depends on Reynolds number, which again is this quantity, rho F, omega F, B squared over 4 eta, just requires you to know the viscosity and the density of the fluid in which it's immersed. B squared and omega F, which is the frequency that you measure in the liquid. So this last formula for K1 is a very celebrated formula because for years there was no other reliable way to measure cantilever stiffness. It's elegant, easy to use. If you go to John Sater's website in Sydney, he's got a nice applet that computes this for you, so you can use it. Of course, it's elegant, easy to use, but it needs to be modified when you're looking at higher eigenmodes and so on. Okay. The second method is the thermal method, which for a long while was not very popular because it was not easy in AFM systems to get the thermal spectrum. Okay? So this uses a completely different idea, and that's statistical physics, statistical thermodynamics. It's basically the law of equipartition of energy. So when you have an oscillator sitting in a thermal bath, it is known that every degree of freedom or every eigenmode, every normal mode of the structure that's in thermal equilibrium must contain in it an energy equal to 1/2 kBT, where T is the absolute temperature, Kb is the Boltzmann constant. So this is a fundamental theory from statistical thermodynamics. So Hutter and Beckhofer said, well, all we need to do is the following. We can measure the 1/2 kx squared. This would be the mean square of cantilever deflection is x squared, right? And multiplied by 1/2 cantilever spring constant. This would be the average kinetic energy of the oscillator, equated to 1/2 kBT. Temperature we know. Kb is a constant of physics, so you can back out Kc from it, right? But you need to know what this requires you to do is to measure the mean square deflection of the cantilever as it just sits in a thermal bath. Butt and Jaschke came later and said that this is fine, except you have to realize that the cantilever doesn't have just one mode, it has many modes. So you cannot just calculate the xt, the mean squared of cantilever deflection is not a good measure. You have to measure it separately for each eigenmode. So what Butt and Jaschke did is they said the way to do it is to get at this quantity xt squared, the mean squared of it, you need to collect the thermal data, which is when the cantilever just sits, it's just vibrating, bombarded by molecules around it. You take the time series data and you do a power spectrum of it, right? That's what is shown here, is a power spectrum as a function of frequency. And you get peaks. The peaks are where the resonances are of the cantilever. And there's a basic theorem in signal processing that suggests that if you look at the area under the power spectrum, under a peak, the area under the peak in a power spectrum equals the mean squared value of the signal that's being measured. So if you measure this area under this curve, it is giving you the quantity mean squared of deflection in that particular eigenmode, right? And so you just equate the left-hand side to the right-hand side, and you get the cantilever constant for that particular eigenmode. Now, this is the method. It's really Butt and Jaschke's method that's there now, built in most new AFM systems. Most new AFM systems have the thermal calibration method built in. It's pretty good. It works very well. But there are some issues you need to be careful about. Sometimes, how do you calculate the area under the curve is an issue. If I give the same curve to you and each one of you will give me a different number for area under the power spectrum. So there's an issue. What's the norm for it? How do you decide this? Okay. When you go to higher eigenmodes, you need to know what is the deflection of the cantilever, and that requires you to calibrate higher eigenmodes of the cantilever, which is not easy. And lastly, the spring constant you get from this depends on the location of the spot. if you move the spot near the free end of the cantilever, you'll get a certain number. Someone else comes and focuses it on another location, you get a different answer. So you have to be very consistent as to where you're focusing the laser spot and so on, okay? And then, of course, when you have a very large spot compared to the cantilever width, you're somehow measuring an average stiffness over a wide area of the cantilever, okay? So these are issues to be aware of, and next time, Ryan Wagner is going to be making a presentation on how, when you use these three calibrations and you try to back out elastic modulus of a material or adhesion of a material, how do you take into account all the uncertainties in these processes, errors that you might make in the calibration? Because most people just report an elastic modulus based on a histogram, but there's uncertainty associated with it. So we'll be talking about that next time. All right? Thank you.